Yep. Dev, you're good to go. Whenever you're ready.
So good morning, everyone. My name is Lohar, and my project is titled Quantitative Determination of Optimal X-ray Parameters for CyberKnife Xsight Lung Tracking System using Machine Learning. My supervisors, whom I'm very thankful for, are Mr. Lohar, Dr. Richard, Dr. J. Kendrick, and Mr. Tom. The structure of this presentation, I'm just going to go over the background of CyberKnife, what motivated us for the study, aims, methodology, the benefits of this research, the challenges we might face, and a proposed schedule timeline. So to begin with, stereotactic body radiation therapy, or SBRT for short, is a very popular technique of radiation therapy, which uses large doses of radiation for small tumor sizes, and that results in very strong tumor control. CyberKnife, which that's the most current model, is a type of radiotherapy machine which specializes in SBRT, but also the benefit of CyberKnife is its capabilities for image guidance, where it can take X-ray images throughout the treatment, and using those, it is able to track the motion of tumors. So in this treatment, we're going to be focusing mainly on lung tumors as they're going to be moving as the patient respirates. So the main components of the CyberKnife machine, you've got the treatment head, you've got the treatment couch, then you've got an IR camera, which is able to detect light-emitting diodes that are placed on the patient's chest, and we'll talk about that later. And you've also got your X-ray sources, which shoot out orthogonal KV X-rays, and those are used for your tumor tracking, and they're detected by on-floor X-ray detectors. So as a general surface level patient workflow for a lung cancer patient being treated with CyberKnife, they'll come in, they'll get a planning CT. That planning CT scan is sent to the CyberKnife system, which then transforms it into a digitally reconstructed radiograph, or a DRR for short. Now, this DRR is pretty important because it is used as a template or a reference by the system for tumor tracking. Then, for the actual tumor tracking, there are two key components which are used. So the first component, which is the one on the left, are the X-ray. So throughout treatment, the machine takes X-rays frequently. And the purpose of this is to just locate the tumor in the X-ray images. And there's two pathways that the system uses, which I'll discuss later on. And the second component is actually measuring the amplitude motion of the chest. And that is done by placing light-emitting markers, which is then detected by the IR camera. So these two components are correlated together, and a correlation model is built, which is then used throughout treatment to actually predict the motion and the 3D location of the actual lung tumor based on the X-ray images. So to focus more into just the X-ray images by actually locating the tumor in the X-ray image, the first method that is very popular is fiducial tracking. So specifically for lung cancer patients, gold seed markers are placed in or near the tumor. As you can see in the image, they can be very distinct. You can pretty easily see them, and hence it's easy to track. However, multiple studies have shown that this approach comes with multiple health risks, the main one being pneumothorax and hemorrhage, and some studies even identify fiducial marker migration to be an issue. And obviously, that is very detrimental because it's going to impact treatment accuracy, and it is possible that the treatment head might deliver a dose to healthy tissue. The other approach, which is a fiducial-less and an invasive-less approach, is the Xsight lung tracking system. And this is entirely dependent on the X-ray image. So in this approach, the algorithm compares the DRR, so that's developed from the CT scan. So it compares the DRR with the X-rays, and using normalized cross-correlation, it is able to compare the similarity intensity patterns and determine the 2D location of the tumor on the image. And studies have concluded that this approach has comparable performance to fiducial marker tracking in terms of local control rate, but with the benefit that it's significantly less toxic and it's non-invasive as well. So this research is going to focus mainly on Xsight lung tracking. So as I discussed with how Xsight works, it's highly dependent on the X-ray image. So obviously, if your X-ray image is poor quality, it's going to impact your treatment accuracy. X-ray image quality, there are two main metrics that we measure. So you've got your contrast and noise. And these X-ray image quality is dependent on three imaging parameters, which are set by the RT before treatment. These are voltage, current, and exposure demand. So if you have a look at how these parameters affect image quality, if you have, let's say, for example, a higher voltage, that just means an energetic photon, you're going to have more penetration, but obviously higher imaging dose. However, there's the risk that you're going to decrease lung tissue contrast. If you decrease voltage, then you're going to increase soft tissue contrast, which is good, and you're going to reduce imaging dose. However, there's the risk that you're going to run into insufficient penetration. If you have a look at current in time, increasing current all time, that just means you can have more photons. However, due to the statistical nature of photon emission and detection, that means going to reduce noise, which is excellent. But you have to worry about overheating of the X-ray source and also motion blur if you increase that too much. And if you decrease these parameters, then you're going to increase noise, but there's less photons that you're actually sending out. But on the other hand, you're also reducing the imaging dose. So as you saw, there's a very complicated relationship between imaging parameters and the image quality. So it requires a very careful trade-off. However, the current process in clinic to actually determine these imaging parameters is just a manual trial and error process, where the clinician gets the information about the patient and the tumor from the treatment planning system, and they just do a trial and error method by trialing multiple imaging parameter combinations and seeing just which one gives them the best image quality. So obviously, currently this ends up taking 20 X-ray images until they arrive at the combination, which gives them good image quality. And that is just unnecessary high imaging dose to the patient, but also that just increases the time in the machine and overall reduces patient throughput. Secondly, if the RT is not able to find a parameter combination which gives them good image quality and they end up actually using something that gives them poor image quality, then later on in the treatment, maybe after third or fourth fraction, that might result in treatment interruptions and hence cause more discomfort to the patient, but also reduce the efficiency of the clinic as well. There's also lack of guidance to the clinicians because the only support that they're provided is an example starting point provided by the manufacturer. And even the manufacturer has stated that the user is responsible for adjusting these parameters based on the patient size and tumor final location. Therefore, a new process needs to be determined that it be able to predict and compute optimal imaging parameters that is highly tailored to the tumor and patient features. So this field of imaging parameter optimization has been done in both the radiotherapy and diagnostic field. So the most relevant study when it comes to CyberKnife has been performed by Nano et al., where they directly investigated the impact of imaging parameters on XLTS accuracy. And in their study, they did conclude that there is an optimal range of imaging parameters that is highly dependent and influenced by the patient and tumor characteristics. There was another study by Miyamoto where they directly investigated the optimization of imaging parameters for tumor tracking. However, they did this on a LINAC-based radiotherapy system and not CyberKnife. And similarly in the diagnostic field, multiple older studies have explored the optimization in, let's say, chest radiograph and mammography, where they just irradiated phantom with multiple imaging parameter combinations and just determined which one gave them the best image quality. So to summarize the gaps in the literature, there's three main gaps that I identified. The first one, that the optimized image parameter optimization that was performed was done empirically and on phantom measurements. And the issue here is that they're limited by the feature space. So if they tried 4 combinations, there is a possibility that there might be an optimal imaging parameter that they have not tried. The ones that weren't done in phantoms were done on non-CyberKnife machines. And thirdly, the literature that was on CyberKnife, specifically the XLTS, only explored the accuracy of the XLTS and compared it to fiduciary marker tracking, so they didn't really focus much on optimization of imaging parameters. Therefore, to optimize the imaging parameters based on the patient characteristics and the human characteristics to result in accurate localization, we can use machine learning to retrospectively study and analyze past patient data and build a machine learning model that's going to be able to predict the imaging parameters. So this can be divided into 2 key aims. The first aim is going to be selecting the relevant features out of all the feature space. So this is important because, as I'll explain later on, some features have a direct and a strong impact on result-based accuracy, whereas some don't. And also in a general machine learning approach, the quality and the number of features we use to impact the performance. Therefore, we're going to use multiple feature selection methods to select the relevant features. And secondly, once those features have been selected, we're going to train and build a machine learning model and evaluate it on real-life cases. So to expand further on the first aim, we're going to begin with extracting all the patient and tumor-related features from the treatment planning system And hopefully, if possible, also take out the image parameter logs, the number of images taken in those treatments, so that we can compare later on how many images were taken in the manual process and how many were taken if you implement this deep machine learning model. Then we're going to do some general exploratory data analysis, and this is important to really understand the data set that we'll be working with, also just observing outliers, patterns, and distributions. Then we're going to apply multiple feature selection methods. You got Pearson correlation, lasso, random forest approaches, and combine these rankings to get a subset of the feature space and get the relevant features. Now, as I mentioned before, this is an important step because multiple studies have shown that some specific features have a direct impact on the attribution. So a key study by Bahit et al. Determined that tumor size, volume, and density out of 18 other features that they explored had a direct impact on XLTS tracking. And also another study by Lee et al. Explored the effect of volume change in fractionation. And similarly, they determined tumor density to be highly correlated with tracking success and also location. So these studies are really helpful because they can be used as a baseline as well when we get our features. So once we have our relevant features, we're going to be predicting and building our model. So I'm just going to follow a very general and well-accepted machine learning training framework. So splitting the data into a training, validation, and testing set. And I will train multiple machine learning models. So you've got basic ones like polynomial regression, but also some advanced ones like support vector machine regression, and also some deep learning approaches like neural networks. Then I'll be able to evaluate the performance of each of these models on the test cases, and then the one with the highest performing will be chosen. This study is going to result in 3 key benefits. The first and the most obvious one is just reduced dose. So because it'll be able to hopefully replace the manual selection process, the RT would not have to take 20 images just to get to the same point. So in this approach, the optimal starting point for the image parameters will be determined, and hopefully the RT will only have to fine-tune those parameters and maybe only take 3 to 4 more images to get to the acceptable X-ray image quality. And by the manufacturer, they have provided that the XLTS system delivers roughly 0.1 to 0.5 milligrays of external surface dose per image pair. So obviously reducing that from 20 images to hopefully 5 is going to reduce the number of imaging dose. Secondly, we're going to reduce treatment errors because treatment errors are frequently caused in XLTS treatment by using a poor X-ray image quality. So if you already start with strong imaging parameters, then you're going to have good image quality and lower chance of treatment errors. And thirdly, this approach is just going to introduce objectivity into treatment planning and reduce any random errors as well. The challenges in this research that we might face are mainly 2 key ones. The first one are stemmed from machine learning approach, which is essentially just the data size, because data size has a direct impact on the performance of your machine learning model. But this is just going to depend upon the number of cases we're going to have access to once we get our ethics approval. And also, secondly, what features are we going to actually have available to us and which ones can we actually extract? The second issue with the second challenge that we might face in this research is just going to be the actual quality of the ground truth. Because when we're going to train the machine learning model, we're going to use a training set and the optimal parameters that the RT ended up using for treatment. However, those optimal parameters that the RT chose are really dependent on the RT's judgment. They're very subjective as well. So then this introduces label noise and label bias as well, because some RTs might really enjoy, or not enjoy, but use high contrast images, whereas other ITs might not really choose high contrast images. They might say, okay, this image quality is fine and should work as well. So this ground truth problem can be identified when we do the exploratory data analysis. We'll be able to see the distribution of the imaging parameters and also the features. And also with the issue of data set size, if we don't have access to a lot of patient cases, then we can try to create artificial data to screen phantoms as well. So as a timeline, we're going to firstly obtain UI approval by the end of this month. Then we spend a couple of months collecting the data, pre-processing, performing our exploratory data analysis, then spend around 2 months for feature tracking and selecting our feature set. Then we're going to train the different machine learning and deep learning models and see which one performs the best. And if there is time, I'll also be able to explore an interaction use case, which is essentially if the tumor features changes throughout treatment, are we able to use the model that we built through between treatment, let's say after the fourth fraction, and change and update the imaging parameters? Because currently the imaging parameters stay constant throughout the entirety of treatment and don't adapt to the changing tumor characteristics. And after that, just finalize the thesis and final presentation. So to conclude, there are two approaches which are used for tumor localization in lung tumor treatment in CyberKnife. The first one is neutral, what we know is invasive, has pelvis, and there's the risk of market migration. The second approach is XLTF. However, there's only a manual selection approach, which results in high imaging dose and tracking errors. We're hoping to replace that with a model that is going to predict the optimal imaging parameters that is tailored to the patient and the tumor. And that's hopefully going to reduce the imaging dose and also reduce treatment errors as well. I'd like to acknowledge the following people. So Mr. Millard for all the insights, Dr. J, email replies, Peshman for the ongoing support, Mr. Tom for submitting the ethics approval and also letting me sit on CyberKnife QA, Neil and Foster for discussing and suggesting ideas for feature selection, and also just the methodologies research group for the feedback to the research meetings. Thank you.
Dev, so you mentioned the size of the data set as a potential limitation. How much data do you expect to be able to use? And I guess to follow on from that, how much data would you like to be able to use?
So we're aiming for which that's what we put into these right.
Okay.
But it is possible to extract more if you use the marker specific.
Do you think you would need more than that to build your machine learning models?
I guess that is going to depend on which model I'm going to train, because different machine learning and models just use different data. So I think generally the machine learning model is not really an issue, but if I'm going to train like a neural network, that just requires a lot more data. Yeah. So it's going to depend on that.
Any other questions?
Yeah. I may have missed it. Do you plan on, are you only going to be using the DRRs and the radiographic images, or are you going to be also taking the planning CTs and associated contours?
Oh no, so I'm going to be extracting, or not extracting, but just taking the actual quantitative features that are already in the treatment planning system. So I'm not going to extract it from the images themselves. So stuff like tumor volume, tumor density, and all that stuff will already be quantified. But you're going to take those values and train those.
Okay. So I was just thinking, like, for your planning CT, for example, the size of the patient, which may or may not be in the dark one, better,
Yeah.
be useful for training such a model. So
I
you
think so,
can
yeah.
actually extract other features that may not be in the image itself.
Yeah. So that also kind of goes back in to the secondary engaged solution presentation, but with the interaction use case. If you want to do that, then you have to extract the features that I want from the actual images themselves. That kind of goes into the radiomics field and extracting just from images. But this project will mainly focus on data, which is already quantified. Right. Yep. But that's the feature work. Yeah.
One question regarding the second challenge that you mentioned about the label bias.
Yeah.
Right. How are you going to mitigate this risk?
So what I realized is that we can't really mitigate it, but we can identify it if it is going to have a huge impact. Because when we do the X-ray data analysis, we can see, is there a general trend with the imaging parameters, let's say for voltage, that there's specific, like 10 or 15 patients that only use a higher voltage, but with another set of patients which have similar patient features, but they use a lower voltage. So we can identify if there is some sort of random noise or some sort of patterns with these. And in the thesis, probably discuss if that could have a potential impact on the model, but it's going to be difficult to really mitigate because that is the only available information that we have.
The question with your patients,
Yes.
is it specific site or group of patients that you are selecting?
Yes, so the ones that have been treated just the Xsight.
Start across anatomical,
Oh, just for lungs.
just not, yeah,
It's the XLP is only focused on lung.
and across the lung in terms of
Sorry.
location of the tumour
Yeah.
across the lung.
Yeah.
the whole lung.
Yeah, no, one. So it's central growth.
Time for maybe one or two quick questions from online. Martin?
Yeah, thanks, Dev. That was a great presentation. I've got so many questions and we're running out of time. Perhaps just this one. So you mentioned that the RTs sometimes adjust the parameters and re-image multiple times to try and look for the best, most visible set. Do those images get stored, and are they accessible? All the test ones that they take?
Yeah, so when I discussed this with Tom, those images are stored, and that's what I've also listed in the methods as well. So we hopefully, if they are stored, which according to Tom they are, we can take those images out and again use this for analysis.
Great.
Congratulations.
Yeah, so just one consideration about the sample size. Since you'll be needing a lot of sample size for training the models, one thing to consider is that when you're extracting the data from the patient data extractor, it will take 15 minutes just to de-archive for each patient. And when you're getting the patient factors from, I mean, I'm assuming you're getting it from Mosaic. So that also takes quite a few months because it has to be taken from all the documents. So, so yeah, just factor that into your timeline. It could take longer than what you mentioned in your timeline. So yeah.
So it's basically just factor into your timeline that the data collection might take a bit longer than you anticipate because it's from clinical reports.
Right.
Yeah.
Thank you.
Thanks, Felicia. We're struggling a little bit to hear you on the microphone, but I'll relay it. Okay. Thank you, Dev. Well done.